Hello dear students, welcome to SAIMEDHA Koti Hyderabad. Now I am going to discuss an important topic in communication known as random variable. Many students feel difficulty with the concept of random variable, but I am very much confident that after listening the lecture you will fall in love with random variable. So let's start the concept of random variable, but before defining random variable I want to introduce some basics. What are those basics? Let's start. The first basic is how you are going to define the term called experiment. How you are going to define. See, experiment I can define like this. Experiment is nothing but a procedure we perform that produces some result. So, experiment is a procedure we perform that produces some result. What are the, and experiment is denoted by capital E, denoted by capital E. What are the examples for experiment you can give? Tossing of a coin is an experiment, rolling of a dice is an experiment, right? So, first example is tossing of a coin, rolling of a dice, These are all the examples for experiment. After this, let us look at the second definition which is required. Outcome. How we are going to define this outcome? Possible result of an experiment is nothing but outcome. Outcome is the possible result of experiment. Possible result of experiment is nothing but outcome. Example, getting 1 when a dice is rolled, or getting a head when a coin is tossed, right? So, getting a head when a coin is tossed, this is one outcome, and getting a number 1 when dice is rolled. So, this is one more example for outcome. And the next definition is sample space. Sample space is nothing but set of all possible outcomes. What is sample space? Set of all possible outcomes. Set of all possible outcomes. For example, when a dice is rolled, what are the outcomes we can get? 1, 2, 3, 4, 5, 6. If you are going to enclose all these outcomes in the form of a set enclosed by curly brackets, that becomes sample space. Now, when a coin is tossed, we may get a head, we may get a tail. These are the possible outcomes. If I enclose all those outcomes in the form of a set using curly braces, yes, it becomes sample space. Sample space is nothing but set of all possible outcomes. And the next definition, what I want to discuss here is event. How we are going to define this event? Event is nothing but subset of sample space. Subset of sample space. Okay, so denoted by C, denoted by some C. And examples for event are getting an even number when dice is rolled. So example, getting an even number when dice is rolled. Dice is rolled. See, getting an even number means when a dice is rolled I may get 2, 4, 6, and clearly this event is nothing but subset of sample space. Subset of sample space. Now, after being comfortable with these definitions, hope you are comfortable with these definitions. Now, let me tell you how many types of sample space exist. Sample space is divided into two types. Sample space is divided into two types. Continuous sample space and discrete sample space. See, continuous sample space means we'll have continuous values here. Discrete sample space means discrete values. See, examples for continuous sample space are temperature readings. See, whenever you are going to record the temperature, see, there is no guarantee that always we will try to get a discrete value which is an integer. We will get continuous values also, non-integer values also you are going to get. So continuous means non-integer values, here integer values, right? Temperature readings, height measurements, comes under continuous sample space, whereas discrete sample space, example is rolling of a dice. Discrete sample space. See, whenever you roll a die, there is no chance of getting 1.5, which is a non-integer value, right? So here in the case of continuous we may get integer values, non-integer values combination, but here we'll get only integer values, right? So examples are here temperature readings, height measurements. Here examples are rolling of a dice, right? Now, after being comfortable with the sample space, let me give you one more important definition for understanding the concept of random variable, which is nothing but function. So how you are going to define the term called function? I can define like this. Function is nothing but mapping between two sets. Function is mapping between two sets based on a relation. So function is nothing but mapping between two sets. Mapping between two sets based on a relation. Suppose if I have a function like this, f of x is equal to some x square plus 1. So here I am going to take one set x and I am going to take one more set f of x. Now how you are going to map? Here 1, 2, 3, here I am taking. What happens if I substitute the value of x to be 1? Here I will get 2, here I will get 5, and here I will get 10, no? Yes. So that 1 is mapped to 2, 2 is mapped to 5, and 3 is mapped to 10. Whenever you are going to map like this, we are going to form a function. So mapping between two sets based on a relation is known as function. And in this function, here the values taken by x is known as range, and values taken by f of x is known as sorry, values taken by x is known as domain, and values taken by f of x is known as range. So here I can write values taken by x is known as what? Domain. Domain. And values taken by f of x is known as range. And between this domain and range, see, we can have one-to-one function. One-to-one means where each value of a domain will map only to one value in f of x, which is nothing but our range. So we can have one-to-one relation, we can have many-to-one relation. Many-to-one relation. Suppose if I am having -1 here, so -1 whole square plus 1, that will also map to 2. So many-to-one is also a function. Many-to-many. Many-to-many is also a function, valid, but one-to-many is not a function. One-to-many is not a function. So remember, always whenever you are forming a function, you must keep in your mind that we can have one-to-one, many-to-one, many-to-many, but we cannot have one-to-many. So this is all about the concept of function, and I hope that you are comfortable with this definition, right? After this, let me define our random variable. Random variable. See, what is this random variable? So before going to define this random variable, we'll see an example. First of all, let us perform an experiment. Experiment is tossing of a coin. Tossing of a coin. What is the sample space? We may get head, we may get a tail. This is our sample space. And let me tell you that, see, the points what we are having here in the sample space, these are known as sample points. These are known as sample points. Alright. Now here what I want to do is, I want to form a function. Just now we have seen how to form a function. Now I want to form a function based on some rule. Rule is my wish. My wish is that if head turns, I'll define a function and map it to 1. If head turns, I'll define a function and map it to 1. And if tail turns, I'll define a function capital X and I'll map it to 2. Right? Now, if head turns, so this head and tail are known as what I said? Sample points, and they can be denoted like this: lambda 1, lambda 2. Lambda 1 and lambda 2 are sample points. Right? Now, if head turns, what is my rule? What is my rule? If head turns, I'll map it to 1. If head turns, map it to 1 like this. Map. If tail turns, I'll map it to 2 like this. Right? So we formed a function. No, this is nothing but the concept of random variable. This kind of function what we formed is nothing but the concept of random variable. Random variable. Alright. So rule can be your wish. See, if head turns, you can map it to 200. If tail turns, you can map it to 1 crore. 1 crore. Right? So rule may be your wish, but if you are whenever you are going to form a function, you must keep in your mind that it must lie in these 3: one to one, many to one, many to many. Hope you understood this example. So I'll do one thing. I'll tell you one more example also. After that, we'll come to a definition. And one more thing is, here random variable is capital X. This rule is nothing but random variable. Okay. Now random variables are denoted by capital letters, and the values taken by the random variable are denoted by small letters. Okay, let me write that point. Random variables are, random variable is nothing but a function, are denoted by capital letters, and the values taken by random variable are denoted by small letters. Small letters. Hope you understood this one. Alright. Now let us look at the next example. Again, in order to gain the confidence on random variable, let us perform one more experiment. Experiment is tossing of two coins. So if you toss two coins, what is the sample space? Head, 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 tail, tail, head, tail, 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 tail. And random variable we have to form. Random variable means some function we have to form. And remember here random variable is formed by taking the number of heads into consideration. Taking the number of heads. So these are sample points, no? These are sample points. So lambda 1, lambda 2, lambda 3, lambda 4. Right? Now our rule is based on the number of heads. So 0, 1, 2, 3. So look here. Head, head means two heads. So two heads, map here. Okay. Head, tail, one head. Map here. Tail, head, one head. Many to one can be a function. Tail, tail means map to 0. So this is a random variable. Here this is a random variable. This function what we formed here is nothing but a random variable. So here x of lambda 1 we formed, x of lambda 2, x of lambda 3, x of lambda 4. Right? Now in order to understand or in order to gain confidence on random variable, let us perform one more experiment. See, experiment is that two coins are tossed. Again, two coins are tossed means tail, 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 head, head, tail, head, head. These are the sample points, right? So, and the sample space is discrete sample space, no? Yes, these are the sample points. Lambda 1, lambda 2, lambda 3 and lambda 4. Now, in order to form a random variable, we must define a function. Function is number of heads plus 1 whole square. Function is number of heads plus 1 whole square. So here how many heads are there? So 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. Now this is the rule. Number of heads plus 1 whole square. Tail, tail means 0 heads, 0 plus 1 whole square. 1 whole square is 1. This is x of lambda 1. Okay. So here tail head, head is 1. Number of heads are 1. 1 plus 1, 2. 2 whole square, 4. Map here. Here also the same. Allowed many to 1. Here how many? 2, 2 plus 1. Number of heads are 2, 2 plus 1 is 3, 3 whole square is 9. Like this. Right? So this is nothing but our random variable. Random variable denoted by capital X. Basically, dear students, random variable is a function of the sample points. Basically random variable must be denoted like this, is a function of the sample points, but here what we'll do is we'll remove this lambda, and denote like this, right. So random variable is denoted by capital letters and the values taken by the random variable are denoted by small letters. Now this example we have seen, and this example also we have seen. So in the three examples what we have seen, we are forming a function, right. Now how you are going to define the random variable? Now can I define like this? Random variable is a function whose domain is sample space and whose range is some set of real numbers. Yes, that is one definition of random variable. So let me define the next slide. So random variable is a function whose domain, because a function will have a domain and a range, whose domain is sample space and whose range is set of real numbers. Okay, this is one definition, or I can give other definition also, that random variable is a function which maps the sample space to the points on the real number line, which map the sample space to the points on the real number line. So these two definitions can be taken for defining random variable. After this, we'll discuss how many types of random variables do we have. Random variable category is divided into three types. Discrete random variable, continuous random variable, and mixed random variable. Right? And the types of random variable, discrete, continuous and mixed, can be explained by the range they are taking. Remember, for a discrete random variable, range is discrete. For a continuous random variable, range is continuous. And for mixed random variable, range is discrete or continuous. And the domain of a discrete random variable. Remember, discrete means value, continuous means range of values. Discrete means a particular value, continuous means a range of values. So here random variable means mapping must be done. Means range is discrete, means a value. So value means what? Domain can be discrete, discrete to discrete, one to one, okay, and domain can be continuous also. Continuous means range of values. Means many to one possible. So remember, the range of discrete random variable is discrete, whereas domain can be discrete or continuous. Now the domain of continuous random variable. So here range is continuous. Continuous means some range of values. So here many are there. Many means many can be only the function. So domain must be continuous. It cannot be discrete here. If I am having discrete one to many, no, not possible. Here you need not worry much here. You can neglect this mixed random variable domain. Discrete or continuous here. Discrete or continuous, but with specific conditions will come here. So domain discrete or random variable, discrete or continuous, but here domain is discrete means this discrete cannot be mapped to continuous. Some conditions will come here, right? Fine. So the types of random variables are discrete, continuous and mixed random variables. Now after this, let me define the next definition, which is nothing but probability mass function. Probability mass function. Probability mass function, right? What is this mass function? In order to understand this probability mass function, this is written as PMF. Observe here. Let us conduct one experiment. Tossing of a coin. I may get head and or I may get a tail. Right? Now let us form a random variable. For defining a random variable, I need one more set. And my rule is, if head turns, I'll map it to. If head turns, I'll map it to 1. And if tail turns, I'll map it to 2. 1, 2. So form the random variable. Form the random variable. So I form the random variable. Right? Now, probability mass function. How you are going to define? See, probability mass function means probability that the random variable takes a particular value. Takes a particular value. Probability mass function means probability that the random variable takes a particular value, right? Denoted by Px of x. P capital X of small x, and is defined as probability that the random variable takes a particular value, right? Suppose if I ask you what is Px of 1? Px of 1. So what is the probability that the random variable x takes the value 1? If the random variable x has to take the value 1 means head has to turn. Head has to turn. And what is the probability of getting head? 1 by 2. 1 by 2. And if I ask you what is Px of 2? Nothing but probability that the random variable x takes the value 2. So if the random variable has to take the value 2 means tail has to turn. And what is the probability of getting a tail? 1 by 2. So in other words, I can say that probability mass function gives the probability distribution of the random variable. Probability mass function gives probability distribution of the random variable. Probability distribution of the random variable. Right? Now we can draw this one also. Here Px of x as a function of x. See, what is Px of 1? It is 1 by 2. No, 1 by 2 means here give a small strip here. Small strip of height 1 by 2. Here also Px of 2 is also 1 by 2. No, small strip of height 1 by 2. In this way you can draw your probability mass function, and this probability mass function will have two properties. will have two properties. They are, the first property is probability mass function always lies between 0 and 1, always lies between 0 and 1, and the second one is, if you add or if you take the summation over this PMF, probability mass function, summation over the I, Px of xi, this is nothing but 1. So 1 by 2 plus 1 by 2, 1. Alright, so these are the properties of probability mass function, but there is a disadvantage with probability mass function, that PMF can be applied only for discrete random variables. PMF cannot be applied for continuous random variables. So disadvantage is that PMF is applied only for discrete random variables. It is applied only for discrete random variables. It cannot be applied for continuous random variables. Means we cannot analyze the probability distribution of continuous random variables using the concept called probability mass function. Then what is the remedy? The remedy is that we are having an alternative definition known as cumulative distribution function, which can be applied both for continuous random variables and discrete random variables. So let us discuss that cumulative distribution function. So the topic of the discussion now is cumulative distribution function. Remember that this cumulative distribution function is denoted by CDF. It also gives the probability distribution of the random variable, but can be applied both for continuous random variable and discrete random variable. Can be applied to both continuous and discrete random variables. Can be applied to both continuous and discrete random variables. Now, how we are going to define this cumulative distribution function? Denoted by capital Fx of x. This is defined as the probability that the random variable capital X takes the values less than or equal to small x. This is the definition of cumulative distribution function. So in order to understand this better, we will do one thing. Let us perform one experiment. Experiment is the same, tossing of a coin. So we will get a head and a tail. Now I want to form a random variable. In order to form a random variable, we must have one more set and mapping must be done. And the mapping is, if head turns, map it to 1, if tail turns, map it to 2. This is a random variable. So we form the random variable also. What is our rule? If head turns, map it to 1, if tail turns, map it to 2. Right? And if I ask you from this, what is the probability that the random variable x takes the value 1? So P of x is equal to 1. If the random variable has to take the value 1 means head must turn 1 by 2. And Px of 2, what is the probability that the random variable x takes the value 2? 2 means tail must turn 1 by 2. Right? After this, hope this. Now, let us find out the CDF. What is Fx of 0? Fx of 0 is nothing but the probability that the random variable x takes the values less than or equal to 0. The random variable is taking the values from 1. Less than or equal to 0 means 0. If I ask you Fx of 1, how we are going to define? Probability that the random variable x takes the values less than or equal to 1. Less than or equal to 1 means 1 it is taking. What is the probability that the random variable takes the value 1? 1 by 2. What is Fx of 1.5 if I ask you? probability that the random variable x takes the values less than or equal to 1.5. Less than or equal to 1.5 means only 1. It is taking the value 1, which is nothing but 1 by 2. Fx of 2, probability that the random variable x takes the values less than or equal to 2. Less than or equal to 2 means, less than or equal to 2 means it can take 1, it can take 1 or it can take 2. So 1 by 2 plus 1 by 2, 1. Fx of 3, probability that the random variable x takes the value less than or equal to 3. Less than or equal to 3 means up to 2 only it is taking, so 1 and so on. Alright. Now, can I put all this in the form of a single expression? Yes. Fx of x is, I can put like this, 0, 1 by 2, 1. So, when the cumulative distribution function is taking the value 0, x less than 1, x less than 1. Now 1 by 2, 1 less than or equal to x less than 2, and 1 x greater than or equal to 2. Can I write like that? Yes. Now I can draw also. How you are going to draw? This is fx of x, this is 0, this is 1, this is 2. See, x less than 1, this is x less than 1, fx of x is 0. At 1, we will have a sudden jump. We will have a sudden jump from 1 to 2. The value is 1 by 2. 1 by 2. And at 2 also we will have a sudden jump, because at 2 its value is becoming 1, and it will continue. It will continue. And this is the shape of our cumulative distribution function CDF. And you can notice here that what is this height? This height is 1 by 2, which is nothing but the probability that the random variable x takes the value 1. And what is this height? This height is also 1 by 2, which is nothing but the probability that the random variable x takes the value 2. Right? So height of this jump, or in technical terms we will call this as discontinuity. Sudden rise or sudden fall is termed as discontinuity, no? So height of this discontinuity is equal to the probability that the random variable x take this particular value. So p of x is equal to 1. This height 1 by 2, this is the probability that the random variable x takes the value 2. Can I write like that? Yes. Now we will do one thing. In order to understand this cumulative distribution function better, we will discuss one more example. And the next example is 3 coins are tossed. 3 coins are tossed and random variable is formed based on number of heads. Okay, form the CDF. Form the CDF means cumulative distribution function. Right? Now how you are going to form? First of all, 3 coins are tossed. Means you must be ready with your sample space. Tail, 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 head, tail, head, tail, head, tail, 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 head, 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 tail, head, 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 tail, head, head, head. How many? 1, 2, 3, 4, 5, 6, 7, 8. Yes, 3 coins are tossed means, this is a sample space. Sample space denoted by capital S. 3 coins are tossed means how many outcomes? 8 outcomes. Now, random variable is formed based on the number of heads. Means if I want to form a random variable, I must take one more set. So 0, 1, 2, 3. Now let us form the random variable. Random variable. So based on number of heads means here 0 heads, here 1 head, here 1 head, here 1 head, 2 heads, 2 heads, 2 heads, 3 heads. So we formed a random variable. Now from this, if I ask you what is, so random variable is denoted by capital X here. What is Px of 0? What is the probability that the random variable x takes the value 0? Means 3 tails must turn. So 3 tail must turn means only one possibility, 1 by 8. Suppose if I ask you Px of 1. Px of 1 means what is the probability that the random variable x takes the value 1? Means this can turn, this can turn, this can turn. 3 by 8. What is the probability that the random variable takes the x takes the value 2? Again 3 by 8. Px of 3. What is the probability that the random variable x takes the value 3? Only this case. 1 by 8. 1 by 8. Alright. So 3 coins are tossed and random variable is formed on based on the number of heads. So CDF. Fx of 0. Probability that the random variable x takes the value less than or equal to 0. Less than or equal to 0. Only 1. 1 by 8. Fx of 1. Probability of x taking the value less than or equal to 1. So 1 by 8 plus 3 by 8. 4 by 8. Fx of 2. Probability that the random variable x takes the values less than or equal to 2. Less than or equal to 2 means this one, this one, this one, 7 by 8. Fx of 3. Probability that the random variable x less than or equal to 3. 8 by 8. 1. Right? Now, can we put this one in a single expression? Yes. Fx of x is 0, 1 by 8, 4 by 8, 7 by 8, 8 by 8. So when it is taking the value 0, if x less than 0, 0 less than or equal to x less than 1, 1 less than or equal to x less than 2, 2 less than or equal to x less than 3. Yeah, and it is 8 by 8 if x greater than or equal to 3, no? Yeah. Now, let us try to draw this one. Zero, 1, 2, 3. How we are going to draw? If x is less than 0, fx of x is 0, 0 to 1, 0 to 1, 1 by 8 means at 0 we will have sudden jump which is equal to 1 by 8, and from 1 to 2, 4 by 8, from 1 to 2, 4 by 8, and from 2 to 3, 7 by 8, and x greater than or equal to 3. Value is 8 by 8, which is nothing but 1. Now here, what is this height is equal to? This is 1 by 8, which is nothing but the probability that the random variable x takes the value 0. What is this height is equal to? 3 by 8. which is nothing but the probability that the random variable x takes the value 1. What is this height? This height is again 3 by 8, which is nothing but the probability that the random variable x takes the value 2. And this height is how much? 1 by 8, which is nothing but the probability that the random variable x takes the value 3. In this way, you are going to form your cumulative distribution function, and I hope that you understood this cumulative distribution function. If you understood this one, let us discuss the properties of cumulative distribution function. Properties of cumulative distribution function. Properties. First property is minimum value of cumulative distribution function is 0, and maximum value of cumulative distribution function is 1. Or we can say that cumulative distribution function value lies between 0 and 1. Cumulative distribution function denotes the probability, so its value lies between 0 and 1. That is the first property. And remember that CDF is a non-decreasing waveform. CDF is a non-decreasing waveform or function, I can say. CDF is non-decreasing function. Remember, dear students, that CDF will not decrease. It's always increase or it will remain constant, but it will not decrease. If anybody says that this is a CDF, you should not agree. CDF will not decrease, it will always increase. CDF is a non-decreasing function. Right. Now the third point is, see, the type of the random variable can be identified based on the shape of CDF. Here, for the previous examples what I considered, see what kind of random variable is this one? Or by looking at the range, you can say no, range is discrete values, means discrete random variable. And what kind of CDF we are going to get? Staircase waveform, stair step waveform or staircase waveform. So look here, CDF, discrete random variable, CDF will look like this, staircase waveform. For continuous random variable, CDF will be a continuous function like this, continuous function. Whereas for mixed random variable, CDF will be combination of continuous functions and jump discontinuities. CDF will be combination of continuous function and jump discontinuities. Right. So by looking at the CDF, we can judge what kind of random variable it is. Right. This becomes the third property. And the fourth property is probability at any point. P of x is equal to x naught. Probability at any point P of x is equal to x naught, or probability that the random variables x takes a particular value. Let me write that. Probability that random variable x takes a particular value, that is P of x is equal to x naught, right, can be obtained from CDF as fx of x naught plus minus fx of x naught minus fx of x naught plus minus fx of x naught minus, and this is for discrete random variable, right, and for continuous random variable, probability of x is equal to x naught is the same fx of x naught plus minus fx of x naught minus. Remember, for continuous random variable, CDF is a continuous function, no, fx of x naught plus and fx of x naught minus, they won't vary much, so that this is 0. This is 0, and this is an important point to be remembered. For a discrete random variable, if you want to take the probability that the random variable x takes a particular value, means fx of x naught plus minus fx of x naught minus, you can verify. We can verify. Suppose if I want to have the probability that the random variable x takes the value 1 here. So this is nothing but fx of 1 plus minus fx of 1 minus. What is fx of 1 plus? 4 by 8 minus fx of 1 minus 1 by 8, which must be equal to 3 by 8. 3 by 8. What is the probability that the random variable x takes the value 1? 3 by 8. Right? So this is the point. And the fifth point is CDF, that is cumulative distribution function, is always continuous from the right. Continuous from the right means fx of x naught plus will be same as fx of x. Fx of x naught plus will be same as fx of x. You can verify. Here. Fx of x naught plus will be same as, suppose here you can verify from this here, what is fx of 1.1? Fx of 1.1, 4 by 8. So what is fx of 1? Fx of 1 is 4 by 8. So fx of, look here, both are same, no? So fx of x naught plus will be same as fx of x, right? After this, sixth point, suppose if you want to calculate the probability, see here, probability of x less than or equal to x is fx of x. Suppose if I want to have the probability of x greater than x, capital X greater than small x, this can be written as 1 minus probability of x less than or equal to x, which can be written as 1 minus fx of x. Seventh one, suppose if I want to calculate the probability over a range, so probability of x1 less than x less than or equal to x2, this is nothing but, I am not going to the proof, fx of x2 minus fx of x1, fx of x2 minus fx of x1, and as the CDF is continuous from the right, I can write like this, fx of x2 plus minus fx of x1 plus, or you can remember like this, here for x2 equal to is there, less than or equal to means plus will come, for x1 not there means plus will come. So here if I ask this one, x1 less than x less than x2, if I ask you, so here for x2 equal to is not there, so this will be fx of x2 minus, for x1 equal to is not there, so minus fx of x1 plus, probability of x1 less than or equal to x less than x2, here for x2 equal to is not there, so this is fx of x2 minus, for x1 equal to is there means fx of x1 minus. right? Now, what is the other possibility? The other possibility would be probability of x1 less than or equal to x less than or equal to x2. So this would be here for x2 equal to is there, means fx of x2 plus minus fx of x1 minus, right? But this is for discrete random variable. For discrete random variable. For continuous random variable, what will happen? For continuous random variables, this plus and minus, they won't make any, they won't make any change. So I can write for continuous random variable, probability of x1 less than x less than or equal to x2 will be same as probability of x1 less than x less than x2, which will be same as probability of x1 less than or equal to x less than x2, which will be same as probability of x1 less than or equal to x less than or equal to x2 for continuous random variable. And one more thing is here, the example what we have seen is a discrete random variable here. Discrete random variable, and the CDF is a stair-step waveform now, and remember this kind of stair-step waveforms can be represented in the form of unit step functions. So for a discrete random variable, I can write like this. For a discrete random variable, fx of x can be written as summation over the I, p of x is equal to xi into u of x minus xi. So CDF can be represented in terms of unit step functions. So this is all about your cumulative distribution function. We can have more discussion on CDF, and sometimes what happens, CDF is not comfortable all the way. CDF is not comfortable all the time. So we are having another another definition known as PDF, probability density function, which also gives the probability distribution of the random variable, but in a different form. We can discuss that later, and I hope that you enjoyed this topic. Thank you.